Okay, let's pick up where we left off. We were about to start number 2 because we had talked about points of inflection. So let's find the points of inflection and intervals over which the function f of x equals x to the 4th minus 4x cubed is concave up and concave down. This will be a slightly easier function to take the second derivative of because it will just be power rule. So first derivative is 4x cubed minus 3 comes down, 12x squared. Now that one doesn't help us with points of inflection or concave up, concave down. Second derivative, 12x squared minus 24x. And I want to know that thing's defined everywhere, but where is it 0? If I factor out a 12 and an x, I'm also left with x minus 2. And again, if two things multiply to 0, one of them has to be 0. So either the x is 0 or the x minus 2 is 0. So we get x equals 0 and x equals 2. So those are our two possible points of inflection. Much like relative extrema, just because they are critical values doesn't necessarily mean they are points of inflection. It has to switch from positive to negative or negative to positive. But we can still make our chart, 0 and 2. A nice number between them is 1. A nice number bigger than 2 is 3. And even negative 1. And again, we're going to plug this into the second derivative. So let's do negative 1. F of negative 1, or f double prime of negative 1. Negative 1 squared is 1, will be 12. 24 times negative 1 will be plus 24, which is 36, but mostly it's positive. When you plug in 1 to the second derivative, you get 12 minus 24, which is negative 12, so that one's negative. And if you plug in 3, 3 squared is 9. 9 times 12, 108. 24 times 3 is 72. 108 minus 72 is 36, so it's back positive here. So what it does show is that we transition from positive to negative or negative to positive at both of these critical values. That means x equals 0 and x equals 2 are points of inflection, but we would really like to refer to them as their xy values in the original. So we need to take these two values and plug them back into the original. So what's f of 0? It's 0. So 0, 0 is a point of inflection. If we plug in 2, f of 2, 2 to the 4th is 16. 2 cubed is 8, so 16 minus 32 is negative 16. So we have 0, 0, and 2, negative 16 are really the 2 points of inflection. And we can also mention where everything is concave up and concave down. We are concave up, where our second derivative is positive. So that would be from negative infinity to 0, and union 2 to infinity. And we're concave down in the middle there from 0 to 2. So even though both of our critical values there were points of inflection, it is again possible for your critical values not to be points of inflection. And additionally, the second derivative provides us something useful. We talked about on the front page that when you're concave down, it's because the tangent line is sitting kind of above your graph. The other thing that we know is that maximums occur kind of when you're turning around like this and you have a horizontal tangent line above the function. So if the second derivative at a relative max or relative min, relative extrema, your critical values of the first derivative, are positive or negative, can kind of determine whether or not you have a relative minimum or relative maximum. And that brings us to what we call the second derivative test. So the second derivative test helps us determine some things about our extrema. So if f is a function and the derivative of the function is 0 at a particular point, the second derivative exists on an open interval containing c. If our second derivative at that point is positive, then it's a minimum at the point in question. If the second derivative is negative, then it's a relative maximum. And if the second derivative is 0, then the test fails and you'll have to revert back to the first derivative test. So here in particular, let's take the first derivative here, f prime of x. So we're finding the relative extrema using the critical points and attempting to use the second derivative test when possible. If not, we'll revert back to the first derivative test. So the first derivative of this is negative 15x to the fourth plus 15x squared. And if we were to factor that, pull the negative 15x squared out, that leaves x squared minus 1. So that should give us when x squared is 0, or when x squared is 1 as critical values, which is 0 or plus or minus 1. So those are our potential critical values. Now normally what we would do in the first derivative test is draw our, make our chart, but there's a fast way to determine whether or not these are maximums or minimums if you don't need to find increasing, decreasing. The second derivative here is negative 60x cubed plus 30x. And if I plug all of these values in, I can maybe determine if they're maximums or minimums. Now what you notice when you plug in 0 here is that 0, this means that it's inconclusive, and we'll have to use 0 in the original derivative test if we wanted to find out if it was a maximum or a minimum. But the second derivative applied at negative 1, negative 60 times negative 1 cubed will be 60. 30 times negative 1 will be negative 30, which is positive. So what that really means is that at negative 1, since this is f double prime of negative 1 is greater than 0, that this is a minimum. Similarly, if we plug in positive 1, we get negative 60 plus 30, which is negative 30, which implies that 1 is a max. Now, to find the actual coordinates of these things, we need to plug them into the original. Now, when I plug f of negative 1 and f of 1 into the original, negative 3 times negative 1 plus 5 times negative 1, or excuse me, negative 3 times negative 1 plus 5 times negative 1 should be 3 minus 5, which is negative 2. So what we would really say is negative 1, negative 2 is a relative minimum. Plugging in 1, negative 3 times 1 to the 5th is 1, plus 5 times 1 should be negative 3 plus 5, which is 2. So we would say 1, 2 is a relative max. To check 0, we'll have to go back to the first derivative test. We don't need to check everything, but I do need to try, say, negative 1/2 and positive 1/2 into the second derivative. Now what you may notice is that when you square, or when you raise a fraction like negative 1/2 to a power, it gets smaller. So x to the 4th is smaller than x squared. What you actually find out is that it doesn't matter. Well, what it does matter, when you plug in negative 1/2 and square and positive 1/2 and square, they're the same when you raise them to either of these even powers. But this is smaller than this one, so both of these end up being positive. And what that means is that 0 is neither a relative minimum nor a relative maximum because the sign didn't change. It actually ends up turning out that the point 0, 0 ends up being a point of inflection, but this allows you to go back and check your relative extrema in the first derivative test if the second derivative test didn't work. But this is really all there is in 3.4, so that's it for this video.